Okay, so this in this video, I'm going to work problems from chapter 3 in chemistry. So I won't be doing everything because it's not all problems. So we'll start with number 2. And number 2 says, what is the mass of the average calcium atom in grams? Okay, so we know the abbreviation for calcium is Ca, and we can go to the periodic chart and find calcium, and underneath the symbol for calcium it says 40.08. So that number tells us the mass of an average calcium atom in AMUs. Okay, and we want to get our answer into grams. So one of the values that you will be given on your test is that 1 AMU is equal to 1.66 times 10 to the negative 24 grams. Okay, so that's just a conversion that you'll be given. So this problem asks us for the mass in grams, so we just have to convert the AMUs to grams. So since grams is what we want to end up with, we'll put this over 1, and then we will multiply, well, we want grams on top, so 1.66 times 10 to the negative 24 grams is equal to 1 AMU. Okay, so AMUs are going to cancel, and the answer that we get will be in grams. We plug those numbers into our calculator. 4.08 times 1.66 raised to the negative 24 power. And what we get is 6.65328 times 10 to the negative 23 grams. Okay, so then we look at significant figures, and we see that we can have 3 significant figures, so this would be 6.65 times 10 to the negative 23 grams. So this is our answer right there. Okay, number 3 says that a specific isotope of nitrogen has a mass. Okay, so now we're given the mass of this nitrogen in grams. It's 2.49 times 10 to the negative 23 grams. And we are asked, what is its mass in AMUs? So again, we know that you will be given 1 AMU is equal to 1.66 times 10 to the negative 24 grams. Okay, so we want grams to cancel because we want our answer to be in AMUs. So we will multiply 1 AMU is equal to 1.66 times 10 to the negative 24 grams. Okay, so grams are going to cancel. So you're going to multiply across the top and divide by the bottom. So it's going to be 2.49 times 10 to the 23 divided by 1.66 times 10 to the negative 24. And the answer that we get is 15 AMUs. So for this particular isotope of nitrogen, the mass in grams is equal to 15 AMUs. Okay, number 4. We are given a magnesium 25 atom. So it's an isotope of magnesium. And we are asked how many protons, how many neutrons, and how many electrons are in this magnesium. Okay, so you should remember that the abbreviation for magnesium is Mg. So if you go to your periodic table and find Mg, the number that is above that is 12. So that's the atomic number. It tells us how many protons magnesium has. Okay, so it has 12 protons, and we know that protons and electrons are equal. So it also has 12 electrons. Then how many neutrons does it have? This number here is called the mass number. And the mass number is equal to protons plus neutrons. So we know there are 12 protons, and protons plus neutrons has to add up to 25. Therefore, there are 13 neutrons in magnesium 25. Okay, number 5. An atom has 5 protons, 5 neutrons, and 5 electrons. What is its symbol, including the mass number? Okay, so the first thing you'll want to do is you'll want to find out which element has 5 protons. So we go to our periodic chart and we find the number 5 and we see the letter B, which stands for boron. So boron has 5 protons, therefore it has 5 electrons. So then what is its mass number? Remember, mass number is protons plus neutrons. So this would be how we can write it like that, or we can write it like this. And the 10 in both cases, both ways it's correct to write it either way, but this is the mass number, the number of protons plus the number of neutrons. Okay, next I'm going to jump down to number 10. And now we are told that you have a wavelength of 231 nanometers. Okay, so that's the wavelength, which is signified by the Greek letter lambda. Okay, and the question asks, what is its wavelength in meters? Okay, so here again, you will be given this conversion. 1 nanometer is equal to 1 times 10 to the negative 9 meters. Okay, so 231 nanometers. Put that over 1. And we want our answer to be in meters, so that goes on top. 1 times 10 to the negative 9 meters over that's equal to 1 nanometer. Okay, so nanometers are going to cancel. So 231 times 1 raised to a -9 exponent, and you will get 2.31 times 10 to the -7 meters. Okay, so and again, this is something you will be given. You just need to know what goes on top and which value you're going to put on the bottom based on what unit you want to end up with. In this case, we want to end up with meters. So this goes on top and 1 nanometer goes on the bottom so that the nanometers will cancel. Okay, let's do number 12. Light, actually, let's go back and do number 11. So I guess I need to, let's see. 231 times 1 exponent -9. So the wavelength that we figured in number 11, or no, number 10, the wavelength was equal to 2.31 times 10 to the -7 meters. Okay, so this is the answer to number 10 that we just did. So then number 11 asks us, what is the frequency of that wavelength? Okay, so if it's this wavelength, what is its frequency? So we know that frequency is equal to the speed of light divided by wavelength. So I'm going to go ahead and put that wavelength in there. And we know, again, you'll be given the speed of light. The speed of light is 3.00 times 10 to the 8 meters per second. Okay, so dividing that. So you have a meter on top and a meter on bottom. Meters divided by meters is 1. So your units that you have are 1/seconds, which is a hertz, and that is the unit that we use for frequency. So 3 raised to an exponent of 8 divided by 2.31 exponent -7. So what we get here is 1.298701299 times 10 to the 15th, 1 per second, which is the same as a hertz. Okay, so then we look at significant figures, and it looks like we can have 3 significant figures. So we have to round here, and this becomes 1.30 times 10 to the 15 hertz. Okay, so that is the answer to number 11. Okay, number 12. Light has a frequency, so we're given frequency as 3.45 times 10 to the 17 hertz. And the question asks, what is its wavelength? Okay, what is its wavelength? So again, our equation is that frequency is equal to the speed of light divided by wavelength. Okay, so we need to solve this equation for wavelength. So I'm going to multiply both sides times wavelength. That gets rid of it on that side, but we have to multiply whatever you do to one side, you do to the other side. And then if we divide both sides by f, that gets rid of the f over here and gets the wavelength by itself. So wavelength is equal to speed of light divided by frequency. Okay, so speed of light is 3.00 times 10 to the 8 meters per second. That's given at the top of the page. You'll also be given it on a test. And the frequency that we were given was 3.45 times 10 to the 17th hertz. And a hertz is a 1/second. So I just want to put it in as 1/second so that we can see what happens to the units. So you have a second on the top, second on the bottom, they cancel, so you're left with meters. And that is that we measure length in meters, so wavelength is measured in meters. So the wavelength that you will get, so 3 raised to the 8th power divided by 3.45 raised to the 17th power, you're going to get 8.695652174 times 10 to the negative 10. Okay, but then we look at significant figures and it looks like we can have 3. So with 3 significant figures, this number is going to become, I'll write it up here, 8.70 times 10 to the negative 10 meters. Okay, so that is the answer to number 12. Okay, let's go to number 15. A photon has a frequency of 1.94 times 10 to the 16 hertz. And then it asks, what is its energy? So a photon is just a package of a small packet of light. And we're given its frequency and asked to determine what its energy is. The only equation we have for energy is that energy is equal to H times F. So E stands for energy, F stands for frequency, and H is Planck's constant. So this is a constant that you will be given, and you're given it there on the top of the page where the problems are. Okay, so we know the frequency. H is a constant, so we can calculate its energy. Okay, so let's, so the value that you are given for H is 6.63 times 10 to the negative 34, and the units are joules times seconds. It might seem like an odd unit, but you'll see in a moment why it's that. And then the problem gave us the frequency. So the frequency is 1.94 times 10 to the 16 hertz, and a hertz is a 1/second. Okay, so then if we look at the units, seconds on the top, seconds on the bottom, those are going to cancel. So the units that we are left with is joules, and the units for energy are joules. So if we do this math, 6.63 raised to the negative 34 power times 1.94 raised to the power of 16 equals 1.28622 times 10 to the negative 17 joules. And if we look at significant figures, we can have 3. So this would become 1.29 times 10 to the negative 17 joules. So I'll write the answer up here, 1.29 times 10 to the negative 17 joules. That's what the energy of that photon is equal to. So that's number 15. Let's look at number 16. So in 16, we're given the energy and we're asked to determine its frequency. So at E is equal to 1.19 times 10 to the negative 16 joules. And we are asked what is its frequency. Okay, so again, the equation that we have is that energy is equal to H times F. So we just need to rearrange this equation to solve for F. So if we divide both sides by H, okay, so then we get EH, E divided by H is equal to F. Okay, we're given E. E is 1.19 times 10 to the negative 16 joules. And F is that, or H is that constant. And you'll be given that constant. H is equal to 6.63 times 10 to the negative 34, and the units are joules times seconds. So again, let's look at so we have a joule on top and a joule on bottom. Joules divided by joules is 1. So your unit's going to be 1 over seconds, which is a hertz, and hertz is what we measure frequency in. So if we do this math, we'll get 1.7948711795 times 10 to the 17th. Okay, so with 3 significant figures, this becomes 1.79. So the units is 1 over seconds, which is a hertz. 1.79 times 10 to the 17th, 1 over seconds, which is a hertz. So that's the answer to number 16. Okay, number 17. Orange light has a wavelength. The wavelength is equal to 612 nanometers. What energy does it have? Okay, so we're asked to find energy, and remember energy is equal to H times F. So we know H because that's a constant, but we don't know F. However, we do know that F is equal to c divided by wavelength. So since we know the speed of light, we know the wavelength, we can calculate frequency. Once we know the frequency, then we can plug it into this equation and we can calculate the energy. There's one step we need to do before that, however. We need to convert the nanometers to meters. So 612 nanometers, and we're going to put that over 1 because that's what we're converting. And we know that 1 times 10 to the negative 9 meters is 1 nanometer. Okay, so nanometers cancel. So 612 times 1 raised to the negative 9 exponent. So this length is 6.12 times 10 to the 7 meters. Okay, so that's the wavelength. Okay, now we can use that number to determine the frequency. Once we know the frequency, we can then determine the energy. Okay, so frequency is equal to c divided by wavelength. Now we know both of those values. The speed of light you are given, 3.00 times 10 to the 8 meters per second. And the wavelength that we just calculated was 6.12 times 10 to the negative 7 meters. Okay, so meters divided by meters is 1. So it's going to be 1 over second, which is a hertz, and that's the unit for frequency. So what we will get for frequency then, so 3 raised to the 8 power divided by 6.12 raised to the negative 7 power, and you will get with 3 significant figures, 4.90 times 10 to the 14, 1 over seconds, or hertz. Okay, so that's the frequency. And now that's not our final answer because the question asks us for energy. So now we can use the value, the number that we got for frequency to determine energy. So energy is equal to H times F. H is a constant. It's given as 6.63 times 10 to the negative 34 joules times seconds. And we'll multiply that times the frequency of 4.90 times 10 to the 14th, and this is 1 over seconds. That's what a hertz is. So seconds are going to cancel, and you're left with joules, and that is the unit that energy is measured in. So energy, if we do that math, 6.63 raised to a negative 34 power times 4.90 raised to a positive 14 power, and we get, with 3 significant figures, you will get 3.25 times 10 to the negative 19 joules. Okay, so this was a problem where we were given wavelength and asked to find energy, and we had to use that wavelength first to determine the frequency using the equation that frequency is equal to the speed of light divided by wavelength. So we used the wavelength to determine the frequency. Once we knew the frequency, then we can plug that into this equation to get the energy. Okay, then number 18 will be the last one we'll do. So number 18 says that a photon has an energy. So E is equal to 2.17 times 10 to the negative 18 joules. And it says, what is the wavelength? Okay, so this problem is similar to the last one. So we're given energy, and now we're asked to determine the wavelength. Well, the equation that we have for energy is that energy is equal to H times F. So we can't directly determine wavelength. However, if we determine frequency, then we can use our equation that frequency is equal to C divided by wavelength. We can solve for wavelength then to if we know the frequency. So let's start over here and solve for frequency. We'll just divide both sides by H. Okay, so E divided by H is equal to frequency. So E was given 2.17 times 10 to the negative 18 joules, and then H is a given value. You don't need to memorize it. It's 6.63 times 10 to the negative 34, and that's joules times seconds. Okay, so you have a joule on the top and a joule on the bottom. Those cancel out, and joules divided by joule is 1. So you have 1 over second, which is a hertz. So that's the frequency is going to be 2.17 raised to a negative 18 power divided by 6.63 raised to a negative 34 power will give us, with 3 significant figures, the frequency will be 3.27 times 10 to the 15. 1 over seconds, or hertz. Okay, so now we know frequency. Now we can use this equation to determine the wavelength. So I'm going to take this equation and I'm going to solve for wavelength. So I'm going to multiply both sides by wavelength. That gets rid of the wavelength on that side, but now I need to get rid of the F on this side. So I divide both sides by F. So wavelength is equal to C divided by F. Okay, we know that C is the speed of light. And the frequency that we calculated over here, right here, is 3.27 times 10 to the 15th hertz, which is a 1 over second. Okay, so here's a second on the top, a second on the bottom, so you're going to be left with meters, and we measure length in meters, so wavelength is measured in meters. So 3 raised to the 8th power divided by 3.27 raised to the 15 power, and you will get 9, with 3 significant figures, you're going to get 9.17 times 10 to the negative 8 meters. Okay, so that's our answer. Okay, so again on this one, we were given energy and asked to determine the wavelength. So it's a two-step process. In order to determine wavelength, you first have to know frequency. So the first thing we did was solve this equation for frequency. So E divided by H is frequency, and then once we had frequency, then we use the equation frequency is equal to speed of light divided by wavelength. We knew frequency and we knew the speed of light, and so we solved for wavelength. Okay, so that is it for the types of problems that you will need to be able to do from the review questions in chapter 3.